Okay, so I owe you a little bit on adjunctions. All right, so now I need to give you the official definition of an adjunction. And so let me just kind of, so adjunctions. Okay, so the idea was if we're given two functors, f and g, from two categories, right? So we wanted, okay, so the idea was that we wanted this Hom, right? So we wanted a bijection here, x. Okay, so this is what we want. This is an adjunction. Okay, so for every x and y, we need this map A of x, y, right? So this is a bijection between these two sets. So we want so for every and this is one thing of what this is what I've been telling you what an adjunction is. But what I haven't told you is how it behaves. So this thing behave, but we also need to behave well with respect to maps. Morphisms. So we have x to x prime in C and y to y prime in D. So it's like not only the compatibility condition, right? So like there's a really long diagram. Okay, so there's a really long diagram that you can do. Does it do this? But it's functorial, okay? And I will explain what that means, okay? So, but to set this up, I need to give some things, okay? So I need to give you the opposite category. I need to talk about products of categories. I need to talk about natural transformations, and then we can get to adjunctions, okay? So first I need to do the opposite category. In contravariant functors. Okay, so I'm going to tell you what a new category is. So given C as a category, so what you can do is you can define C op. So this is the opposite category of C. C. And so the objects here, so these are objects of C. They're the same objects. C. And then a morphism. So a morphism in the opposite category. So maybe we can just like color them, right? So we could call them like we could call them like x op if x is in there. So then a morphism x op to y op, right? So it's just you flip the arrows, right? Is a morphism. So where you take a morphism y to x in C. So here the arrows are, all you do is that the arrows are flipped. Okay, sometimes we, sometimes we just, we won't do this op thing, and we'll just, write it with arrows flipped. Okay, sometimes we add the op when it's ambiguous. We want to be extra clear, but sometimes they get in the way, and it's not the best way to write things. Okay, so this is what the opposite category is. So now let me tell you what a contravariant functor is. So what's a contravariant functor? Oh, let me see. I think I'm okay. Okay, so contravariant functors. Okay, so a contravariant functor is a functor from the opposite category. So definition, a contravariant functor from C to D is a functor. Let's call it F from C op to D. Okay, so this is what a contravariant functor is. Okay, some people just say it's a thing, so it's just a functor where the arrows get reversed. So this is a functor from C where all the arrows get flipped. But the one way, the trick about doing this opposite category thing is like you pre-flip them and it makes the notation cleaner. So functor from C where all the arrows get flipped. Like, so the composition goes backwards, right? So it's like, f of f composed with G is f of G composed with f of f. If f and G are morphisms in C, not C op. So this is for morphisms in C. Okay. So that's what a contravariant functor is. So let's give you an example. So this is the most important example. Okay. So if it's the co-representable functors. Okay. So if y is an object of a category C, then consider this functor h superscript y from C op to sets given by, it takes an object x and it maps it to, okay, well, we'll write the notation here, but this is just C from x to y. Okay, so the idea is that okay. So now we need to show that this is contravariance, right? So the contravariance is here. Okay, so given a map in the original category, so if we have x1 to x2, let's see if we have space. Yeah, we have space. We'll move it up. Okay, so if we have a map here from x1 to x2, if we call this, say, phi, right, in the original category C, so what I need to do is I need to produce a map, okay? So now we have x2y, and we need the arrows to flip, okay? C to x1y, okay? And this thing is sometimes called phi star, okay? So how do you do this? So this takes f, a morphism, and it maps it to phi star f. This is the pullback. And this is defined to be, okay, so this is defined to be f composed with phi. So let me just kind of we did this once for the other HOM, the one where we did the representable functor. So this is what's a co-representable functor, okay? So we're doing the HOM sets the other way. And in this case, right, so let's see what we have, right? So let's just write this again, C of x2, y. And we need, so given one of these, right, we need to produce one of these. And f is a map from x1 to x2. Okay, so we have a map from x1 to x2. Sorry, phi is a map from x1. We have a map from x1 to x2, right? And then we have a map from x2 to y, right? And we need to produce a map from y to x1, right? So this thing was part of the. This was given here, right? And then we had this. This was our map f, Okay? And then what you do is you just compose the two. So you do phi compose with f. And this is what's called phi star f. And this is the pullback. Okay, and you'll note that phi star of f composed with g is phi star of g composed with phi star of f. So that's like the contravariance. Okay, so wait, is that right? So let's see. No, I mean, I don't think this makes sense. So sorry, let's not bother with this right now. Okay, so yeah, the way it goes is that the way it goes is that phi 1 composed with phi 2 star is phi 2 star composed with phi 1 star. Right, that's what I wanted to say. Okay, so if I had two of those maps, right, then that's what would happen. Okay, so yeah, this is another way of writing that is that this is hy of phi 1 composed with phi 2. And this is hy of phi 2 composed with hy of phi 1. All right, that's what that is the co-representable functor. Let me just say a word. There's a very important theorem called Yoneda's theorem that will appear later. Okay, now I need to define products of categories. Okay, so given two categories, we need to define the product category of two things. Okay, so given given two categories, so C cross D is a new category. This is the product category. C and D. These are two other categories. Okay, and the objects. Okay, so maybe I'll have to move up again. So, but the objects of this category, right? Well, there are pairs of objects where X is in C and Y is in D. So it's just like you'd expect. Okay, and so the morphisms are pairs of morphisms. So it's exactly like you'd expect it to be. So xy to x prime y prime, right? If I have f and g, right? So these are pairs of morphisms. So are pairs of morphisms. So here f x to x prime and g y to y prime, and they compose as you would expect in the usual way. Okay, so now I've defined contravariant functors. I've defined products of categories. Okay, so I need one more thing, and that's natural transformations. Okay, so right, so natural transformation. So what's a natural transformation? Okay, so now we have categories, we have functors, right? Okay, and now we can, so we had the category of categories, right? And the morphisms in the category of categories were functors, okay? I'm going to go, it's like Inception. We're going to go one level deeper. We're going deeper. So now we're going to do morphisms between functors, okay? So the category, so the category of functors, so let's say the collection of functors between two categories. Fun CD of functors between categories C and D forms a category. Okay, so so this is okay. So these are functors. Okay, so this is the category of functors. So the objects, right? So the objects are functors, right? F from C to D, and just as a reminder, that means that if you have a morphism, x1 to x2, so this is a morphism in C. Okay, so this is in C. So then you get f of x1, and then you get a new map f of f, and you have f of x2. Okay, so that's what a functor does, right? So here are the objects of this category. They're the functors. Okay, and so now the morphisms, okay, so morphisms, so given two functors, these are called natural transformations, right? So morphisms of functors are called natural transformations. Okay, so what's a natural transformation? So given, so yeah, so let me just write down what a natural transformation is. So if f and g are functors, so let's say they're functors from C to D, right? Then what we'll do is we get a collection of maps, so a natural transformation, and we have a special symbol for it. So a natural transformation, phi. Okay, and now I'm going to do the cool symbol. It looks like the implication symbol. So the natural transformation is a collection of maps, is a collection of morphisms. Okay, so we have, let's say, f of x, and we'll call it phi of x to g of x, where x ranges over the elements of C, or all the elements of the category, so all the objects, such that, all right, so whenever you have a map, okay, such that the following diagram, this is the following very important diagram holds. So if I have a map here in C, okay, if I have a map here, so this is a morphism in C, right? Well, I can apply one functor, right? And I get this thing. And I can apply another functor, and I get this thing. Okay, so those are the two functors, right? And then I have the natural transformation that compares the two. Okay, so this is the way to get a morphism between functors. So what you do is, for every object, you link them up with some morphism, but they have to be compatible. Then we call this functor. It has to be functorial in this way, right? So that's what a natural transformation is. So it has to be functorial. Okay, so all right. So now we have objects. And so now I can tell you what an adjunction is. Okay, so adjunctions, the official definition of what an adjunction is. Okay, so here's the definition. So okay, so let's just kind of think about this for a moment, right? Okay, so here let's look at these two things that we want to compare. So let's think about this. So kind of like a scratch work here. So here we have this this is how we've been talking about adjunctions, right? We have this comparison between these two things, d of x, g, y. Okay, so so this functor here, so it's contravariant here. So contravariant in this component. right? And so this, it's also contravariant in this component here. So if I were to write it like this, right? So this is also contravariant in that component, all right? And then it's covariant. So that's the word we use for like ordinary ordinary functors, right? And so it's covariant in the other component, right? So these things here. So if I were going to write it like this, this x blank here. So it's covariant in these things. It's covariant with respect to morphisms here. Okay, so I think I know how this is going to go now. So this is supposed to be the following. So both of these define functors. Okay, so now we can give a definition of the adjunction. Okay, that closes out the scratch work here. Okay, so we're going to have to make this a functor. We're going to have to make these things functors. Okay, so there's two functors that we're going to write down. And then we're going to say in an adjunction, so this is a of xy, is going to be a natural transformation between those functors. Okay? So given okay, so these are functors. So an adjunction right, is a natural transformation between the functors. Okay, and so now we know that it's contravariant in the first component, and it's covariant in the second component, and this goes to sets. Okay, so is a natural transformation, let's say A, right, between the functors here, and we go xy. This thing goes to C f of x y. Okay, and the other one takes xy, and it maps it to, well, the other one, d x g of y. Okay, so we could call this one, say, h f and hg or something, right? Because this is like covariant in the g, and let's see, maybe I want to do that the other way. So yeah, we'll do that the other way. Oh, I don't know. I mean, it's debatable which way you want to put it. I don't know there's no really standard name that I know of for these things. Okay, but this is the definition. So this is an adjunction. Adjunction's a natural transformation between these two things. Okay, and so now I'm going to write the diagram, and hopefully I'm going to write out what the compatibility is. Okay, so I'm gonna draw the video now I'm gonna draw the compatibility condition, right? So like there's a really long diagram. Okay, so there's a really long diagram that you can do.